Hello, this is Emmeline for the final sprint. Let's go ahead and start with revisiting old problems. I'm going to address this first bullet point now, but I'm going to address this second one when I talk about problems I found while creating my game. So starting with that, I do have bullet factories and tank factories, and I have a scene in which bullets and tanks and enemy tanks enter in and out of the scene, calling their scene entry and scene exit when appropriate. So let me go ahead and load that up and play this for you. So you can see in this scene that I have a bunch of bullets, and in a second enemy tanks will start spawning. Okay, and then I would like to address my tank's jitteriness on screen as well. It doesn't look as jittery as a higher frame rate, but that's just because I can't regulate when my camera updates in relation to my tank. So if my tank is moving forward and my camera moves forward a frame later, you get this jittery effect even if the tank is moving smoothly in of itself. The camera is always a frame behind and then jumps up to the position of the tank, and it creates this jittery effect. I understand now this is a kind of situation where a scene graph would be really useful, because I would like the camera to always update its position after the tank updates its position, but clearly that's not the case, and that's why we see this jitteriness on screen. But here you can see that I have bullets effectively entering and leaving scenes along with enemy tanks. As for the second point for the scene class, if I come over here and go into the engine files for scene management, scene, here you can see it's a pretty sparse class, like you said, and it just calls the processing of all the managers. I have the registration broker first, and then update, and then draw is called down here. If we look into Bluebird in the order those are called, and here my Bluebird manages my visualizer and then my screen log, and that's not at a scene level. I do that at a higher level. And that's also so my Bluebird can manage that the wireframe is set for the visualizer, and that solid is set for everything else. For my camera manager, you saw over here that it is, or let me go into my scene. You can see here it is a scene level manager. The scene has access to what camera is being set, and if we go into the camera manager, it has a default camera, which it is responsible for. It also holds the orthographic camera for the sprites, and it's in charge of deleting those two cameras, but it's not in charge of if you set the current camera, it's not in charge of controlling that camera, as you say over here. Did I just? Yeah. My time manager, I have my tanks moving related to time now, so they require time on the first frame. Or I've tested that they require time on the first frame. And then I do have a God cam, which moves around. I have my God cam is in my demo files, not in my engine files, just because it's a really rough, it's not like a perfect test tool. It's just been for my testing during the building process. So I have that in my demo files, and it's not an actual engine feature. Yeah, so if I press G, I can fly around in my God cam. For the collidable system, here we have the overall class diagram. We can see we have the collision test and the three derived ones for terrain, self, and pair. Over here we have the collision dispatch. Down here we have the collision. If I can scroll down, we have the collision volume right here with the overall collision volume. Here we have collision box volume, and here we have this is the AABB, and this is the OOBB, which both are derived from the collision box volume, and over here we have the B-sphere volume. If we come over here, we have a collidable group, which has a pointer to its group AABB. Up here we have the collidable, which has a pointer to its own collision volume, which can be any of these types, and a pointer to its own B-sphere, and then its then a pointer to the model that is passed. If we come over here and look at the actual collidable, here we have the enum. If we look in here, we can see you can set the collider model and takes in the type, and then since the user shouldn't be doing this often, I just have the if else, or this basically a switch statement in here to do that. And then for that you initialize the volume. Let me come over and look at this. So if we come over here, you can see in here what the B-sphere, the only data members it needs to hold are its own center and its own radius. Then if we look at the OBB, oh, sorry, all the methods are in box. They need a max. Both of these need a max, a min, and then I have them hold their world and their world inverse, so we don't have to recompute it, because that's something we need for switching spaces. Then they both have a scale factor, their half diagonal, and their world center. So if we look inside of those over here, you can see when a volume box is first initialized, we set it to the values that stay the same for a OBB. And then if we go into the, is this right? Oh, that's a B-sphere. If we go into here, whenever compute data is called on an OBB, the world center, the scale factor, the world and the world inverse are recomputed, but the half diagonal isn't, because that stays the same from the beginning, and neither is the min or the max. But if then we look into AABB, we can see whenever you need to compute data, you need to recompute the max, the min, and the world diagonal, along with these other things. And also notice that we don't compute the world inverse for the AABB every frame, because we don't need to do the same space switching when we do the intersect tests. Yeah, and then we clearly have the intersection doing the visitor pattern down here in all of these. And if we look into math tools quickly, we can see in here we have all of the different pairs for each of the intersections. We could probably collapse, I haven't done it obviously, but we could probably collapse these two into the same one and just doing it if a box is colliding with a box, because the code inside of both of these is pretty much the same. So that's one change I could make here, would be to collapse these two into the same one, so they're both one. If a box is colliding with a box, we could use the same code, but that's not the case. And then if we move on to the collidable groups, right over here. Now we compute. Here we have the computation for the AABB, so we go through all the collidables in the collection, and we get the collision B-sphere, and we can compute the data using. So if we go to this function here, we can compute the data for an AABB using a B-sphere. And this function is specifically for computing the group AABB, because it expands the already existing AABB by the B-sphere by getting the max between the sphere and the current max, to expand the AABB to fit all of the different B-spheres that was given. So that's for updating the group's AABB. And then let me show you that is only done once per frame if we go over to the collision manager. Yeah, so here in process elements, and then here we can talk about this in a second, but here you can see once per frame for every collision ID we compute the AABB. And then if you notice here, I do a if check to see if I need to compute the AABB, because with the way that having the static works currently and the collision volume, when you change scenes, the collision groups stay, but new has not necessarily been called on the collision groups, because that happens when you register. So continuing on with collision, as I said here, I now understand when I'm reading this grading document how a collision system would be beneficial in this case. So when a new collabable group would be created, it could register itself to have its ABB updated. Clearly I didn't do that. I'm doing this if check instead. That is definitely an improvement I could make here, but not something I currently have implemented. But the AABBs are only being updated once per frame. Moving on to the collision testing. Here we have the base command, so nothing going on there. And we do the train command. So for all of the candidate cells, so you get all the cells that need to be tested against by requesting them from the train. And then for every cell, you test it against the B-sphere, and then you test it against the collision volume, and if both of those intersect, you get a collision. For the self, obviously you don't test it against the AABB, but you do test it against the B-sphere, and then against the collision volume for each, and then you process that callback. And it's the same for the pair test. Let me open that up real quick. Here we go. So for this one, you do the intersect. You test one person's B sphere against the whole group AABB. Well, first, sorry, this was off the screen. You do the whole group AABB against whole group AABB, then B sphere against AABB, and then B sphere against B sphere, and then collision volume against collision volume. So they're all the tests for that. Now for my visualizer, I had the pool and factory working at the end of last quarter, but let me go ahead and show that to you. So here you can see my visualizer. You create the commands. You create commands. That's all cleaned up at the end. I'll show you later that my memory's clean. And then it comes back and it shows down here when you call process commands, and it calls execute on those. Then you call render collision volume back over here, and that, once we get through all these little pass-throughs, that renders the collision volume by setting it the world, the matrix, and then renders it. Let me go ahead and run this demo for you. Things I've added to my visualizer is you can now show lines, you can now show train cells. So here I have the train cells underneath each graphics object being lit up, as well as the normal underneath the main tank being highlighted. Yeah, so let me get over to this hill so you can see that the normal aligns. And we'll come back and look at this demo when we're actually talking about train. But as you can see now I have lines. There are markers on my boxes in the max and min corners. Yeah, so that's pretty much how my visualizer improved. It has been with lines and markers and the boxes, obviously, because we only had B spheres last quarter. Now let's take a look at my math tool. Here you can see I have the intersect functions for all the different types of volumes we have. You can combine two vectors and get the max combine or the min combine, get max of just floats. You can get centers. I can check for interval overlap between two intervals. There's some clamping functions and some other random distance functions for like projection and intersection. If we look in here, you see all these functions are like, I think the longest one is this one. It's technically one line, but it's for all the different, it's for the 60 different axes pairs. But all of these are pretty short, pretty straightforward. Now for the terrain, let's start by looking at the class diagram for that. So you have the train object manager, which you load and get the trains from. You have the train here, which is kind of like the graphics object before the train. So it has the texture, the shader manager, and the train model. And then you have the train manager, which points to the current terrain. So if we start by looking at the train object manager, here you can see I have the documentation for that in my asset section. For the get train, I show you that once you've loaded a train, you can retrieve it anytime, or you can load it directly to the scene using set terrain. And then down here I show you how to load the train, and I have all the parameters laid out for what you need to do to load that. For the actual data inside of a train object, if we go back to the class diagram, let me view code. If we look in here, all you have in here is the pointer to the train model, the texture, the shader, and the world matrix for the train. So this acts a lot like a graphics object. And then I actually have one more level down, which is the actual train model. So that holds the actual model of the train, and then it just holds a few values like the side length, the pixel width, the length, and the cell width, just so these don't have to be recomputed super often. I have a lot of helper classes, one's to show collision, one to test intersections with the train. So, and then the barycentrify classes. If we go ahead and look at what a train cell is composed of, it's just the train coordinates, which is just a I and j value. So it's 2 ints and 2 floats is what a train cell it means for me. So it's the coordinates and then the max y and the max and min y. Let's go back over here. Yeah, so just a few floats and few ints. My train model is the graphics object that holds the model. I don't hold on to any of these arrays, as you saw. And then I showed you my data structure. And then I showed you I have a ton of internal methods, including my barycentrify method. I can go from a vec position to a cell, a coordinate position to a cell, and then a point, so the I and j, to a cell. So now let's look at how collision works for the train. So you come in here and you get all the candidate cells. So you get a rectangle area for the collision. So you pass in a collidable and then it returns the collection, the train rectangle area. Then you iterate through that rectangle area. And the way the rectangle area is defined is it's just a begin iterator, an end iterator, and then incrementation in between those two iterators. And if we look into what makes up an iterator, it's just 3 train cells, and like I said before, a train cell is just 4 floats. So an area is really defined by around like 15 or so floats, makes up whatever area of train you need, and then you iterate through all of those cells, and you test intersection between a B-sphere in the cell and then the actual collision volume in the cell, and then you say if it's actual collision inside of these intersection classes. So the intersect brings you to the train object, which holds the train model, and then what this does is it takes the cell that you're giving it and it turns it into an AABB. So this one actually doesn't intersect between a sphere and a max and a min. And then if you see down here, if you're doing a collision volume, it does the visitor pattern. So it comes in, and so a train model only holds one collision volume, and that one collision volume is used for the entire train. So it sets that collision volume to be the one it needs at a time, and then it does the collision between that collision volume and the collision volume that was just passed into it. And it passes that on to the next model using the visitor pattern. So once again, you go from the test command, you go into this train model, and then this train model sends it to the other collision volume, or it sends it directly to BB Math Tools. And then this one will eventually send it to BB Math Tools as well. All the work that's done in the train model is specifically related to getting the cell of the train, so it's not doing collision processing in here. Now for the final bit of terrain, let me show you that train collision is safe if you drive off all 4 sides of the train. So I've left the last level of my game. I haven't been clamping the player's position, so I could demonstrate that you are able to drive off the 4 sides of the train. Oh, I'm not. Let me build this real quick. Super fast build time brought to you by Obscure Compiler Setting. Let's go to scene 3. You can see I'm already off the edge of the board. I made this especially short just so I can show you that I can drive off all edges of the train and the game's not gonna freak out or crash or anything. Yep, and that is all for train. Next, for my documentation, if you remember last quarter, I had the first couple steps for making your new game and getting started in Bluebird. The only major changes I've made in these steps in here have been changing them so they're now compatible with the DX, so that's redoing all the graphics stuff and making sure that all the inputables is using the correct keyboard and not the Azul keyboard. So that's all been changed over. If we go in here, I've added documentation in the Bluebird API for the window settings. So that's all the stuff for controlling the window, which I now have because of DX. for time management. I think most of that was here last quarter. In game objects, collision has changed a little. We're now just in setup. You have the collider type here. You can click on that and you can see the different types of collider types, and I also say it in the description for how to collide. And then for the graphics system, this is all new. So in graphics objects, it lists all the different kinds of graphics objects, including a skybox, and it outlines the necessary functions that you have to use or the ones you have to overwrite to create your own graphics object. If we go into terrain management, this is all it says in here, but it tells you how to load it and then how to set it inside of a scene. If we look inside of loading, it outlines what all the parameters are, and exactly what you need to do with them. This is also where you can see the load and load all resources for this. These are for all my assets. And light management, if I go ahead and click on this for light management, I have examples and descriptions for how to clear lights, how to update lights, and getting lights. And here's all of this. I have all of the parameters set out for updating lights and what they do. In asset management, the only new thing is the terrain object manager, which I just showed you, how I have the load outlined for that. If we come down here. And then the scene looks pretty much the same from there. I think that's all for new documentation for this quarter. Let me double check with this. Oh yes, and then also the demos that I have. If we go over here, we can go into this folder, then to my student folder here, and these are the same demos I had last quarter, except for ported over for my new graphics engine, so they have nice lighting in them and everything. And then also in my collision demo, I added the terrain demo stuff is in here as well, and that the terrain demo code I have in here is what I have inside of my terrain documentation. Yeah, so here we have my new it's the new collision demo, and this scene shows how to register bullets and the sphere are all registered as collidables, as you can see from that. And it also shows how to use the barycentrify normals and height to have your object move with the terrain. So that's the update to that demo and to my documentation. Now for my individual project, I have an entire final report in the submission folder that you can look over, but I'll go over it briefly. So my project, I converted to DX11. I implemented a new shader system. I'll talk about later about the optimization-ness of it. So I did that by only setting each shader to context once and then rendering all necessary graphics objects. And I also created a centralized light management system, which really helps usability when it comes to not having to set light in every shader, but only having to set it once in one central light system. So for the DX conversion, my Bluebird now inherits from the DX app class. So run is called in the init app function, which is in the main window. So if we come over here, we can look at that. So in the main window, instead of initializing a new DX app, if we come down here in the init app, it does a new Bluebird app, and then it unloads, it terminates the Bluebird app down here as well. So then inside of a DX application, if we go into graphics, DX main, DX app, we now have a private update scene and a private draw scene, and this is what's called by the main frame tick. So this way, DX app can control when the application's update and draw are called, so it can do the render target switching and the depth clearing all at the right time. There are set rasterizer stage, solid rasterizer stage wireframe, which Bluebird uses to do the visualizer stuff. I don't currently have wireframe graphics objects for the user to use, but I would also use these to implement those, and I'd do it so those are functions I also added. You can also dynamically change the window size. That took a little research on how DX does that, but at any time the user can call set width height for the window, and that will change the window size. And then I created a Bluebird keyboard class, which basically does what Zulkey is, which makes a more usable user interface for getting the keyboard, and it has git key state, which masks the bit mask. I also have sprite rendering going, which you've seen in some of my demos with the orthogonal camera, and then I also had to create image, rectangle, and graphic object sprite classes, which hold all the necessary things for creating a sprite. If we come over here and we look at that real quick, that should be in graphics objects sprite classes. So we have a rectangle, which is just the XY and the width and the height. You'll notice a lot of this looks like the stuff in Azul because I got a general idea of what I should be doing from that. It's a texture. And here you have the graphics objects. The graphics objects all create their own model because they all need different UVs to get the correct part of each texture. So that's the way I'm doing it. In theory, you could do it all with the same model by resetting the UVs every time, but that seemed, I wasn't quite sure how that worked, and this seemed more straightforward at the time. No, that was the right one. Let's get over there. And then I obviously poured over all major functionality. I've had that for a while, but all of that's in DirectX now, so all the expos are over, sprites, strings, and the keyboard. Here's things that are missing. Right now, you can't change the background color as the user, which I'd like to have for my intro screens and stuff, but currently I never looked into how to do that, so that's not a thing. And the user cannot register to receive callbacks from the mouse. So those are things that might be nice to have that I didn't implement. So for my shader system, every frame, graphics objects must call submit render on themselves. That causes the internally to call get shader on itself to get its own shader, and then submit render on that, which will pass itself to the shader. The shader will then will create a render command using that graphics object and add that to a command list, which then when Bluebird calls shader manager process elements, it will then call render on every shader. It then checks to see if toRender is empty. If it's not empty, it will set the shader to context and everything that needs to be done on a shader level, and that's all done in a function called prepare to render. And then after it's prepared to render, it'll go through and call render on all of those commands. So it'll execute all those commands. Something that I ran into while I was doing this was that since you have a render command, each with an individual graphics object in it, you couldn't reuse the graphics objects like you used to be able to by just resetting the world and resending render. So I decided to change my render commands to hold the world matrix as well. However, as I'll discuss in performance section later, I think this caused a major slowdown in my system once you get a lot of graphics objects, because it's necessary to copy this matrix information over in every single render command you're doing, every single frame. So we'll talk about that in a second. But so for the user responsibility, if the user wants to create their own graphics object, they must write the get shader function, which returns the shader that should be used by the graphics objects, and they must also write render, so that's to set them all context and do all that stuff. And then if the user wants to write their own shader, they need to write the prepare to render function, which does everything that the shader needs, like setting eye position parameters, setting the shader to context. But besides that, everything else is handled internally. So originally, I did not plan the separation of what was handled internally and what was handled by the user, because I didn't have the foresight to see what couldn't be generalized for all shaders. But now I do, so I have that render function, I have that prepare to render function, the get share function to generalize, so the same system can be used across all different kinds of shaders. So that's where we get to the performance improvement section. So this goes with the further exploration system. So node management is the system that everyone did where you just set the shader to context every time you render a graphics object. So just brute force, every graphics object has the shader reset to context. Shader management 1 is the one I fully implemented, which actually ended up being less performant with more graphics objects. So that one is you call submit render, and there are render commands created, but also to grant more usability, I also had to copy over a world matrix, which in hindsight probably caused a lot of the slowdown, along with having to manage an entire list, because this had to happen every frame, even though I do have a render command factory, so you aren't using commands and news, you are still adding all these render commands to a list, then clearing that whole list every single frame. And then shader management 2, I did a very rough prototype of, and this is where what we discussed in class, and you were discussing with David, is basically I just did not clear the list at the end of the frame, so you only had to submit to render once, so that's more of a registration system. And so if we look at these performance improvements, you can see starting off with low number of graphics objects, each shader management got better. My shader management I implemented a little bit better than no management. And so with low numbers, you can see setting to context is the bottleneck, but by the time we get up to around 2,000 graphics objects, you can see that in the shader management 1, having to copy all those world matrices and having to manage a whole list of 2,000 objects, clearing it, and then re-adding all of them to that list every single frame, that is causing way more of a slowdown than an improvement. But using the registration system, where all objects are only registered to be drawn once at the beginning of the frame, you see that this causes a much bigger improvement over no management and a much larger improvement over the shader management I currently have implemented. So the conclusion for all of this is that the system I actually implemented this quarter and my final product is slower when you have upward of 2,000 graphics objects than having no management at all. While my actual end shader system, I guess, wasn't successful, I think I learned a lot from this, and I know what kind of shader system I need moving forward and where the bottlenecks are and aren't. And I know, now I know that's just not setting a shader to context every frame doesn't necessarily mean I'm getting performance improvement. So yeah, that's it for my shader system. Next, I'll talk about my light data management. So now for my light data management, quickly before we do that, up here, these are frames per second. I realize I did not make that clear anywhere, but these numbers are how many frames per second I was getting, running each of those systems. Then for my light data management, so as I created the light manager system, I realized there's basically a glorified centralized data management system for all light data. The light manager does not push any of the data to the shaders. The shaders must pull it from the light manager when they want. Internally, the light manager, I could make this dynamic, but right now I have it set that has 20 spots for each time of light source. And the user can update, get, or clear the lights, update, changes the values of the given index, give returns the light object back to the user, a pointer to it, and clear resets the light values to their default values, and these values are made to not have any effect on the scene. So if you don't set any of the lights, there's no lighting on your scene. So if we look back in my original plan, I was planning to have shaders have to register to the light manager to get the light data pushed onto them every scene. However, I realized this design didn't really have any purpose performance-wise or design or clarity-wise. I thought it ended up making a lot more sense for shaders to pull the data from the light manager, because then the shader can decide when it does and doesn't need data without having to worry about registering and deregistering. My personal experience with this during making my game has that this really streamlines making lighting, especially when you're using multiple shaders that all need lights and you want the scene to look like they all are using the same lights. It makes that much easier, and also it has the benefit of you don't have data being copied across multiple shaders, so that centralizes the data and makes the shader objects not have to hold all of their own light data, so it makes them smaller. And then for looking at examples of this, I showed that earlier in my documentation, but if we scoot on over here and look into my demo scenes, this is the wrong demo, excuse me. Down here, if we then look into my scenes, boss battle, we can see here I'm using it quite extensively in my last scene. I'm clearing all lights every scene and then setting a whole bunch of new lights on a timer, and then I'm using a color shader, and then while using the color shader and just the texture shader, all of those shaders get updated because they're all pulling light from this. So that's all for my light management. So now I believe the last thing I have to show you before I'm done with my final sprint is my game, that my memory is clean, and the changes that I've made because of my game. Let's actually start with the changelog. Unfortunately, I wasn't keeping track of the changes I was making while I was doing them, and I have an awful memory, so this is just what I was able to come up with trying to think back on creating this game. I know I've been having I had that issue I brought up in class with using the same train in multiple scenes would cause a registration state error. So I fixed this by forcing the state change at the end of a scene. Now when the drawable manager removes drawables at the end of the scene, it forces them to say deregistered because they are deregistered. Instead of having a weird crash when a texture is not set in a texture graphics object, I added an assert, so the user now gets an assert instead of just a random crash in like random code deep down. You get an assert when it realizes you never set the texture and you're trying to render a graphics object. The game used to crash when you left the train area. As I demonstrated earlier, I have fixed that. This is one that I don't have a solution to, but I've definitely been having issues with, and I brought up way 40 minutes ago at the beginning of my sprint, I brought this up. So when I reuse game objects, currently all my factories are scene specific and aren't used across scenes, and that's because when I reuse a game object between scenes, I run into a lot of issues with registration states, and that's because if you end a scene and the object is registered for update and then you don't have a scene exit isn't able to be called on it because you don't have a scene to submit exit, you end up at the beginning of the next scene when you try to reuse that game object as it having the registrations that I had at the end of the last scene. So a few solutions I was thinking about, and I haven't settled on one, is should the user be allowed to force registration states? And that just seems like a gross overreach of privileges unmanaged. So I'm kind of a big no on that one. So what my draw manager is doing right now, and this is part of my fix to my train problem, is my drawable manager sets all drawables registration states to currently deregistered when it removes them at the end of a scene. And then the solution I'm implementing right now in general for game objects is should I just not be able to use game objects between scenes? Yeah, so thoughts on that one are appreciated, or solutions. So I'm currently using the last method, but I don't think it's the best. And then another one, which you know about, that I came up with was my mesh separator problem that I brought up in class. Was something that came up because I was trying to use that bullet texture, and it wasn't working. So now I'm going to play through the whole game for you, talk a little bit about each level, and I'm going to turn heap profiling on so we can make sure all my memory is clear. So let's go ahead and get started with level 1. So if we press 1, this is target practice. The player is clamped to this area up here. The level ends once you kill all the targets. Let me go ahead and play through it for you real quick. So now we're on level 2. You guys have a few tanks coming after you. You have to kill them all, and then the level's over. Yeah, let me go ahead and kill all these tanks. And you can see they follow you around, they shoot at you, all that good stuff. And they all stick to the train as well. So now we're on to the final level, which is this boss tank level. As well as a few different mechanics. So whenever the boss bullet hits the ground, you can see he spawns a new tank. I have the boss health set really high right now, just so I can be in this level for longer. You can see I have my lights all flashing in this level too. Yeah, so let me play through this one for a little, and then we'll exit out and see if the memory is clear. Also, if you notice, as you get farther away from the boss tank, it shoots farther out at you, so the bullets, they don't track the player perfectly, but they're made to hit nearby the player. So you see there, if I'm way out here now, his bullets come out super close to me. And then if I go ahead and let the boss tank kill me as well, we can see that I'll restart this level and we'll still all be good. Okay, so there I go, I die, and I just start this level over again. Okay, so now let's exit out. I have a breakpoint right there, so I can take a snapshot of the heap. And what you see here, this is just This is the stuff from Rapid XML. Yeah, so you can see besides the Rapid XML stuff, my game is completely leak-free, and I believe that is everything for my final sprint. It's been a great year. I'll see you tomorrow in class.